Imagine if everything we thought we knew about Earth's mass, about its very composition, was just scratching the surface. What if our planet, and maybe even our sun, is actually far heavier, far more complex than conventional science has believed for, well, forever? That's exactly what we're getting into today. We're taking a deep dive into a really fascinating paper, Earth's Dark Plasmaspheres Origins, by J. Alfred, and we're pulling in some other groundbreaking research too. Our mission here is to explore this, frankly, astounding claim that dark matter isn't just way out there in deep space. No, the idea is it's fundamentally part of our solar system, our sun, and maybe even right here, deep inside Earth itself.
Yeah, it's quite something. What's really fascinating is how these new analyses are, well, shifting our whole understanding. Historically, the amount of dark matter right here in our cosmic neighborhood, it's been seriously underestimated, mostly because it just got mixed in, conflated with ordinary matter in the calculations. But the latest data, it paints a very different picture, a dramatically different one.
Okay, so let's unpack this. What are these sources telling us about this hidden mass of our world? Let's jump straight to maybe the most surprising part. You probably think, like most people, dark matter is this distant, mysterious stuff, right? But these sources, they point to something much, much closer to home.
Indeed, they do. There's a 2023 analysis, a really significant one, using neutrino oscillations data. This comes from detectors like IceCube and Super-K, these huge underground observatories. And what they found, well, they estimate that the mass of dark matter in and around the entire Earth could be roughly 20% of the planet's total mass.
20%,
Yeah.
that's like adding another small planet's worth of mass to Earth. And J. Alfred, the author of that main paper we mentioned, he proposes this dark matter exists as a plasma, with particles carrying a sort of weak, dark electric charge, forming what he calls dark plasmaspheres. So, how on earth did we miss something that big for so long?
Well, the idea that we underestimated it isn't actually brand new. The author of our main paper, he raised this concern back in 2007. And not long after, other researchers started thinking along similar lines.
Right. So what were some of those first hints, those early clues that pointed towards this hidden mass?
Absolutely. Well, consider some work from 2008 by Jin-Kao Xu and Jonathan Siegel at the University of Arizona. They looked at the dark matter density around the sun, and they estimated it was about 16,000 times higher than the general estimate for the galactic halo. That's the sort of diffuse cloud of dark matter around the whole galaxy. They calculated that 7.69 times 10 to the 19 kilograms of dark matter had become gravitationally bound just within Neptune's orbit. That's huge, about 300 times more than you'd expect from the background halo level. Their conclusion was pretty blunt, and I quote, "Overall, we find that dark matter in our solar system is far more important than previously thought." And this wasn't just theoretical. It had real implications for detection experiments and maybe even explaining odd spacecraft acceleration anomalies, through gravitational three-body interactions.
So it's not just a theory, it could actually explain things we've seen, like weird spacecraft movements. That's fascinating.
Precisely. And this got more support in 2009. A team led by physicist Stephen Adler at Princeton. They argued that, yeah, those changes in space probe speeds when they flew past Earth, that could be explained by dark matter bound to Earth. Their calculations pointed to densities way, way higher orders of magnitude greater than the general galactic halo. Adler proposed this idea of an accumulation cascade, where dark matter just keeps collecting. This assumes a kind of matter-antimatter asymmetry for dark matter, meaning it doesn't just annihilate itself, allowing it to build up.
Okay, and it wasn't just about stuff stuck to the sun or Earth, right? There were wider galactic hints, too.
That's right. Fast forward to 2012, astronomers at the University of Zurich. They also found that older ways of measuring mass had likely underestimated dark matter. They refined their methods, used thousands of K-dwarf stars near the sun, and their results: a 90% chance that dark matter is much more abundant than we thought. Their work even hinted it might be the first evidence for a whole disk of dark matter in our galaxy, the so-called Randall-Reese dark disk, or maybe just a squashed galactic halo. And Alfred, our main author, suggested most of the dark matter in this disk, especially near ordinary matter, would be self-interacting, having that weak, dark electric charge.
Wow, okay, so we're building a picture of a huge amount of hidden stuff, maybe even in a disk shape. But what about direct evidence, something really tied specifically to Earth itself?
Well, on a more local level, data from GPS satellites actually gives us some compelling clues. In 2014, Professor Ben Harris at Texas University looked at Earth's mass as sensed by satellites GPS, GLONASS, Galileo, his calculations. They concluded Earth has more mass than the official value set by the IAU, the International Astronomical Union. And since ordinary matter couldn't explain the weird accelerations the satellites felt, well, the inference was dark matter. And this fits the bigger picture too. The whole solar system moves faster around the galactic center than it should based on visible matter alone. About 60 kilometers per second or 37 miles per second faster. And that extra pull is attributed to dark matter, affecting everything inside, including Earth.
Okay, right. So it seems pretty clear dark matter is way more common nearby than we thought. It's affecting spacecraft, satellite orbits, even our galactic speed. But where is all this extra dark matter actually coming from? It's not just sitting there, is it?
Not at all. The sources we looked at detail quite a few ways dark matter interacts with and builds up in our solar system.
Let's talk about what you called dark matter weather. I like that analogy.
It's a good one, I think. So physicist Jurg Diamond and his colleagues at UC Santa Cruz, they proposed something interesting. Small clouds of dark matter may be shaped like flattened spheres or cigars, even about 4,000 AU across. That's 4,000 times the Earth-Sun distance. They suggest these clouds pass through Earth regularly. Maybe a million billion of them drift around in the galactic halo. Earth might encounter one every 10,000 years or so, and the encounter lasts about 50 years. But interestingly, they don't seem to mess with Earth's orbit much.
So we're basically sailing through these invisible dark matter rainstorms periodically.
Precisely. And it's not just pure dark matter clouds. There are also regular clouds of ordinary matter that seem to carry dark matter along with them. For example, right now, our Sun and Earth, we're moving through something called the local interstellar cloud. It's mostly neutral hydrogen. We entered it about 100,000 years ago, and we'll probably be in it for another 10,000 to 20,000 years. And researchers like Leo Blitz and David Spergel, they strongly suspect these kinds of interstellar clouds harbor dark matter too.
And our galaxy itself is just a busy place, dark matter-wise.
What? Absolutely. Remember, our solar system is embedded deep within the Milky Way's huge dark matter halo. Sue and Siegel, back in 2008, they estimated that over its entire 4.5 billion year life, traveling around the galaxy, the solar system is plowed through an incredible 203 solar masses worth of dark matter. That's 203 times the mass of our sun. It's immense. Think about it. Every single kilogram of matter on Earth has likely encountered maybe 1,000 dark matter particles every day for over 4.5 billion years. It really makes you think about this invisible sea we're constantly swimming in, doesn't it?
It really does. An invisible sea. And I think I read something about a dark matter highway. Is that a real thing?
Yeah, it's another fascinating idea. Astronomers see the Milky Way essentially eating the Sagittarius dwarf galaxy right now. And as it does that, it strips away stars, gas, and dark matter from the smaller galaxy. Researchers like Heidi Newberg suggest we might actually be able to detect a stream, a sort of dark matter highway, flowing in one direction right through Earth, a literal current of dark matter.
Okay, so it's raining down, it's flowing through in clouds and streams. What about the biggest thing nearby, the sun? Is it collecting this stuff too?
Oh yes, it's thought to be a massive collector. The sun sits deep in that galactic dark matter halo where it's densest. Measurements already show that the visible stars near the sun only account for about half the matter density we expect to be there. And like we said, the sun moves around the galactic core about 60 kilometers per second faster than visible matter alone can explain. That strongly points to a lot of dark matter influence.
So the sun's own speed is a big clue, and it sounds like it's been gathering this dark matter for, well, basically its entire life.
That's the thinking. Researchers at Oxford, even back in 2001, suspected the sun harbored a huge reservoir of dark matter particles. Astrophysicists like Elidio Lopes and Joe Silk, and later Lorenzo Iorio and his team, they argued that massive objects like the sun would naturally capture passing dark matter gravitationally.
So what happens when the sun keeps accumulating all this stuff? What are the consequences?
This is where it gets really mind-bending. Iorio's team, back in 2010, estimated something startling. If dark matter keeps piling up in the sun at the same rate it has in the past, Earth's orbit could actually shrink to maybe half its current distance from the sun over the next 4.5 billion years or so. And incredibly, there's actually some observational evidence that might support this orbital shrinkage. Studies suggesting our orbit is slowly tightening. It effectively means there could be an invisible sun growing inside the visible sun.
An invisible sun. Wow. That changes everything about how we picture our star.
And it gets even more interesting. More recently, physicists Suvir Sarkar and Mads Franson concluded the sun probably contains about 2 to 5% of its mass in dark matter. And again, assuming that matter-antimatter asymmetry, This captured dark matter wouldn't just annihilate, it would build up. It would actually change how heat moves around inside the sun.
Ah, so it's not just sitting there, it's having a real physical effect on the sun's internal workings, like its heat transport.
Exactly. And this buildup could potentially solve a major puzzle in solar physics, the solar composition or solar abundance problem. That's this long-standing issue where the amounts of certain elements observed on the sun's surface don't quite match our models. Computer simulations by Stephen West and Aaron Vincent's team explored this. They showed that gravity would pull light dark matter particles into the sun's core. These dark matter particles could then absorb heat from the very center and carry it outwards to cooler regions, or just ferry heat to the surface more efficiently. This would subtly change the core temperature and structure. Now, these theories often rely on an as yet undetected short-range attractive force, a fifth force, allowing dark matter to interact just enough with ordinary matter to transfer that heat.
A fifth force. That's a whole other rabbit hole. Okay, so the sun collects dark matter. Maybe it affects its heat. Could the sun also be producing dark matter or even blowing it out?
That's another theoretical possibility, yes. Some hypothetical dark matter particles, like axions, are actually theorized to be produced by processes within the sun. There are experiments actively looking for these, like the CERN Axion Solar Telescope, or CAST. And if there is a big reservoir of dark matter inside the sun, you might expect something like a dark solar wind. Streams of self-interacting dark matter particles may be pushed out by dark radiation, guided by dark magnetic fields, just blasting away from the sun. If that's happening, trillions of these particles, axions, maybe dark photons, dark protons, could be washing over Earth every single second.
Incredible. Just incredible. Okay, so dark matter is raining down, streaming through, maybe even blowing out from the sun. But how does it actually get inside the Earth? That's a key question, and maybe the biggest question. How can there be so much of it, like that 20% figure? If our planets seem to follow Newton's law of gravity so perfectly, shouldn't we see weird orbital behavior?
That's a really important point and a common misconception. The idea that obeying Newton's laws rules out significant dark matter is, well, incorrect, according to these sources. Here's why. Historically, when we measured the mass of Earth or other planets, we were measuring the total gravitational pull. We couldn't distinguish between the pull from ordinary matter and the pull from dark matter. It all just got lumped together. Imagine, just as a thought experiment, if the sun and planets were made entirely of dark matter but still had the same total masses we've always measured. They would still follow Newton's laws perfectly. We wouldn't see any weird orbital anomalies just because the composition changed. So the lack of anomalies doesn't actually rule out a large dark matter component. That dark matter would simply be part of the total mass we've measured all along.
Ah, okay, that makes sense. We measured the total effect without knowing the ingredients. So if it's there, what lets it get trapped inside Earth? Why doesn't it just pass straight through like those neutrinos?
Well, while most dark matter probably does pass through, the idea of self-interacting dark matter opens up possibilities. If dark matter particles can interact weakly with ordinary matter particles, perhaps via that hypothetical fifth force we mentioned, causing a tiny attraction, they could lose energy as they pass through Earth. Lose enough energy, and they wouldn't be able to escape Earth's gravity. They'd get trapped. Earth could effectively act like a filter, gradually increasing the concentration of dark matter within itself over billions of years.
And it might not just be stuff we've collected recently, right? It could have been there from the start.
Exactly. Dark matter was certainly around when the solar system was forming. The protosolar nebula moved through that dense Randall-Rees dark disk we discussed. So some embryonic dark matter could have been incorporated right into the cores of Earth, the Moon, all the planets, asteroids, comets, as they formed. A 2023 study actually noted that these kinds of exotic scenarios, like Earth forming around a dark matter seed, are still considered viable possibilities.
Okay, so if it's trapped inside, or was there from the beginning, where would it end up? Where would it concentrate inside Earth?
Good question. Gravity inside Earth is actually strongest near the boundary between the liquid outer core and the solid mantle. So a lot of dark matter particles might get trapped in that region. The author, Alfred, also suggests that if that fifth force exists and causes attraction, then dark matter density might correlate with ordinary matter density, meaning you'd find the most dark matter where ordinary matter is densest, which is deep inside Earth's core. Physicist David Peat even speculated that Earth's core could contain as much as 10% dark matter. And this kind of particle-to-particle correlation Maybe a dark proton weakly interacting with an ordinary proton could explain why mass measurements historically just lump them together.
Okay, this is really shifting the picture of our planet. If the old ways of measuring mass just mixed everything together, how are scientists now able to start separating them? How do they get these new estimates, like the 20% figure? What changed?
Right? How do we weigh the planet more accurately? It's a fundamental question. Traditionally, like we said, Earth's mass comes from Newton's law and measuring gravity, how fast things accelerate towards Earth. We have incredibly sensitive gravimeters that detect tiny variations, but the assumption was always that this gravity came solely from ordinary or baryonic matter. As that 2023 neutrino study pointed out, these gravitational methods measure the sum of dark matter and ordinary matter. They, quote, would not be able to distinguish between the two.
Hmm.
Even seismic waves, which tell us a lot about Earth's internal layers, ultimately rely on assumptions tied back to those gravity measurements. They could easily miss a dark matter contribution.
So, what were the breakthroughs? What are these game changing new methods?
A truly independent approach emerged around 2018 called neutrino tomography. It's ingenious. Using the ice cube detector, that massive sensor array buried in Antarctic ice researchers measured Earth's mass, its core mass, and even its moment of inertia. They did this by observing how neutrinos passing through the Earth from different directions were absorbed or scattered by the material inside. And the key thing here is that neutrinos interact via the weak force, which both ordinary matter and dark matter feel. So neutrinos can effectively see both components.
Wow, using neutrinos to X ray the Earth, essentially, that's a huge step. And it gets even more precise now.
It does. More recently, scientists realized something else. The presence of dark matter inside Earth should subtly change how neutrinos oscillate, how they change flavor as they pass through. They predicted specific deviations from the expected oscillation patterns if dark matter was present. And a 2023 analysis of ice cube data used this. It effectively ruled out more than 32% of the core's mass, or 24% of Earth's total mass, being dark matter. That's an upper limit, established with high confidence what they call the 1 sigma level. Similarly, studies using atmospheric neutrinos at the Super K experiment in Japan set another limit. They ruled out more than 21% of the entire Earth's mass being dark matter, again at that 1 sigma confidence level.
Ah, so these studies set upper limits, but they also constrain the possibilities, leading towards that roughly 20% figure as a likely amount.
Exactly. These independent, non-gravitational methods point towards a dark matter contribution somewhere around 20% for the whole planet, maybe closer to 30% just within the core. And as the source material emphasizes, this is highly significant. It really marks a potential paradigm shift in how we understand Earth's composition.
Okay, so we have this significant chunk of dark matter inside Earth. Now, J. Alfred, the author of our main source, argues it's mostly in a plasma state, forming dark plasmaspheres.
Hmm.
What does that actually mean? Dark matter, plasma, inside a planet.
It's definitely a revolutionary concept. Alfred suggests dark matter inside Earth wouldn't form solid structures like ordinary matter does. Instead, it would exist as these less dense, energetic plasmaspheres. He gives four main reasons. First, self-interacting dark matter particles were thought to be extremely light and small. This means huge distances between them, long mean free paths before collisions. So they don't easily bump into each other and form atoms like ordinary matter does. Second, that hypothetical dark electric charge is believed to be much weaker than our familiar electric charge, preventing strong bonds. Third, these theoretical dark sectors might have a lot of neutral dark matter particles floating around, which would kind of insulate any charged dark particles and slow down interactions. And fourth, he speculates that dark sectors might just be intrinsically hotter, based on ideas about how the multiverse might have evolved.
So not a solid dark core, but maybe these diffuse energetic spheres mixed in with regular Earth matter. He calls them dark Earths, right? If they are less dense, like a plasma, how would they interact gravitationally with the ordinary matter part of Earth?
Yeah, it creates an interesting dynamic to consider. On galactic scales, huge amounts of dark matter clearly shape the distribution of ordinary matter through gravity. But on smaller scales, like inside a planet, things might be different. If you compare equal volumes, this dark plasma would be much, much less dense than solid rock or metal. Ordinary matter gets incredibly dense thanks to the strong electromagnetic force pulling atoms tightly together. Dark matter wouldn't have that advantage. So any dark Earth counterpart would be much less massive within the same volume and contribute less to the local gravity field per volume. In that kind of scenario, the dark matter inside Earth might actually be more subject to the gravitational pull of the denser ordinary matter, rather than the other way around. This actually ties into research by physicist Yang Bai on possible dark exoplanets outside our solar system. He suggests such planets could either be incredibly dense, denser than iron, or so low density they seem almost physically impossible by ordinary standards. And those super low density ones would be extremely hard to detect gravitationally.
What a journey we've been on. We've really unpacked an incredible, almost science fiction idea that our Earth, our sun, maybe every planet and moon, holds a significant, invisible chunk of dark matter. We went from realizing we probably underestimated it for decades to exploring new ways to measure it using neutrinos, revealing that maybe 20% of Earth's mass could be this stuff, accumulating from galactic streams, maybe from the sun itself, possibly even embedded since the very beginning.
It really does highlight how dynamic our understanding of the universe is.
Yep.
New data, new techniques, they constantly challenge assumptions we've held for a long time. And this idea of dark plasmaspheres or dark Earths coexisting within our own planet, it fundamentally shifts our perspective on what a planet even is. It suggests a much richer, stranger, more complex internal reality than we ever pictured.
So, where does that leave us? What does it all mean if our planet, if our sun are potentially teeming with this invisible matter, maybe existing as a plasma, maybe interacting through a fifth force we haven't found yet? What could that imply? For our basic understanding of geology, of solar physics, maybe even life, energy, the fabric of reality right here on Earth, it definitely leaves you with a powerful thought. What else might be hidden right under our noses, in plain sight, just waiting for the right tools, the right questions to finally be revealed?